Hi everyone, this is Dr. Siva Nageswara Rao, working as Assistant Professor of Mathematics in the Department of Mathematics and Management Science. In previous lecture, I explained about what is partial derivative. Like we started with limits, continuity, partial differentiation. In view of partial differentiation, we explained, that is, we studied about first order and second order partial derivatives. Now today I am going to explain Jacobian and functional dependency. Now in view of Jacobian, the definition is given in this form. Let u of x comma y is equal to u of x comma y and v is equal to v of x comma y be functions of two variables x and y. The Jacobian of u comma v with respect to x comma y is defined as the determinant in which first row the partial derivatives of u with respect to x and y, that is dou u by dou x and dou u by dou y. Coming to second row, we will calculate the partial derivatives of v with respect to x as well as y, that is dou v by dou x and dou v by dou y. This is like 2 by 2 determinant, just the difference between product of diagonals and product of the non-diagonals. Therefore, answer is dou u by dou x into dou v by dou y minus dou u by dou y into dou v by dou x. This is how we will find the Jacobian of the given two functions involving two independent variables x comma y. Now we will extend it into three variables. So we will take three functions involving three variables x comma y comma z. So let us take u is equal to u of x comma y comma z, comma v is equal to v of x comma y comma z, and w is equal to w of x comma y comma z, are three functions involving three independent variables x comma y and z. So the Jacobian of u comma v comma w with respect to three independent variables x comma y comma z are given by 3 by 3 determinant in which the first row contains the partial derivatives of u with respect to xyz, second row contains the partial derivatives of v with respect to xyz, and third row we will write the partial derivatives of w with respect to x, y and z. Like this we will form 3 by 3 matrix. We will find its determinant. Next we will see one example on Jacobian, how to find the Jacobian of the given two functions involving two independent variables. Let us take u is equal to f of x comma u of x comma y as x square plus y square. We will write it as u of x comma y and this as v of x comma y. So first we will find the partial derivatives of u with respect to x and y. Similarly, the partial derivatives of v with respect to x and y. So what is the partial derivative of u with respect to x? Denoted by dou u by dou x. On right hand side we will apply partial derivative with respect to x by treating y as constant. So the derivative of x square is 2x. Anyway, we are applying partial derivative with respect to x, y is constant, its derivative becomes 0. Similarly, the partial derivative of u with respect to y is denoted by dou u by dou y. By treating x as constant, x square derivative becomes 0. Therefore, the derivative of y square is 2y. In the same way, we will apply partial derivative to v with respect to x as well as with respect to y. Right. So dou v by dou x by treating y as constant. So x square derivative is 2x. Similarly, partial derivative to v with respect to y by treating x as constant. Hence, its derivative becomes y square. Sorry, the derivative of y square is 2y. It is multiplied by minus. Hence, we will get minus 2y. We will substitute these respective values into the Jacobian, that is j of u comma v by x comma y is equal to determinant ux, uy, vx, vy. Just substitute the respective values of partial derivatives. Here we will get this matrix. Determinant of 2x, 2y, 2x minus 2y. Find the determinant of this 2 by 2 matrix. Difference between product of diagonals together with product of non-diagonals. You will get final answer as minus 8xy. So, this is the process how to find the Jacobian of the given functions involving two independent variables x comma y. Now we will see one more example in which this example contains three functions involving three independent variables x comma y and z. Now let us see. Here our aim is to find this Jacobian of the given functions in which u contains x plus y, v contains y plus z, that is y and z, w contains x, y, z. See here, u is equal to x plus y means it doesn't mean that the variable z is not there. It is already present. But we can write u is equal to x plus y plus 0 into z. 0 into z. So it means what? Z is also the variable involved in u, but it is not present. So it means u is depending upon xyz, v is depending upon xyz, w is depending upon xyz. So we can talk about the partial derivatives of u comma v comma w with respect to x comma y comma z. So the solution is, given that u v w values in terms of xyz, we will calculate the partial derivative of u with respect to x, that is 1, with respect to y, that is 1, with respect to z, 0. In the same way, we will find the partial derivative of v with respect to x, that is 0. Why? Because v is free from x. The partial derivative of v with respect to y, that is, the partial derivative of with respect to y means by treating x and z as constant, the derivative of y with respect to y is 1. Similarly, the partial derivative of v with respect to z is also 1. Now, we will find the partial derivative of w with respect to x by treating y and z as constant. Again, it is 1. Similarly, dou w by dou y is also 1 and dou w by dou z is also 1. Now, we will substitute all these values into the Jacobian determinant. What is the Jacobian determinant? The Jacobian determinant is ux, uy, uz, that is first row, vx, vy, vz, that is second row, wx, wy, and wz. By substituting all these respective values into the determinant, you will get this matrix. Now find out the determinant of this matrix. First row, first column element multiplied by the determinant of remaining 2 by 2 matrix by deleting first row together with the first column. So you will get answer as 1. This is the process how to find the Jacobian of the given function if it is involving three independent variables with the three different functions. Now we will talk about the functionally dependence. In generally, what does it means? Here we will take two or more functions. If you want to say functionally dependence, it means there is some relation between the given functions such that it seems to be one function is depending upon another function. That is called depending upon one function with another function by using the functional relation. So we will call it as functionally dependence. We will define it as, let u is equal to u of x comma y and v is equal to v of x comma y be two functions. If there exists a relation denoted by f of u comma v is equal to 0, it means there is something relation between u and v such that u and v are related, then we can say two functions u and v are said to be functionally dependent. Otherwise, we will say functionally dependence. It means what? By taking two functions, here our aim is to construct a relation between u and v if possible. It is possible, we will say functionally dependence. Otherwise, it is functionally independent. Here, this theorem provides some more information about functionally dependence, how the Jacobian will help to decide whether the given functions are related or not. Now, if we want to say two functions u and v are said to be functionally dependent, if its Jacobian is equal to 0, hence we can create some relation between u comma v. That is what this theorem means. This theorem means if dou of u comma v by dou of x comma y is equal to 0 in a region, then u and v are said to be functionally dependent in that region. Similarly, we can extend same formula for n number of functions involving n number of variables. Here, what are the n number of functions? u1, u2, so on, un represents n different functions involving n different variables. Say x1, x2, so on, xn. If you want to say these n number of functions are functionally dependent, it is enough to show their Jacobian is equal to 0. Now we will see examples. Show that u is equal to x square plus y square and v is equal to tan inverse y by x are functionally independent. Independent means there is no relation between u and v. It is enough to show its Jacobian is not equal to 0. Now let us take the given functions. U is equal to x square plus y square, v is equal to tan inverse y by x. Now we will find the partial derivatives. Why? Because in view of Jacobian matrix, we want first row as well as second row as first order partial derivatives with respect to x as well as y. So here we will calculate dou u by dou x is equal to 2x, dou u by dou y is equal to 2y. In the same way, we will apply partial derivatives to v with respect to x as well as with respect to y. Now, in generally, what is the derivative of tan inverse x? The derivative of tan inverse x is 1 by 1 plus x square. Here also we will use same thing. That is the partial derivative of v with respect to x is, we will get 1 by 1 plus y square by x square. Again, we need to apply partial derivative to an expression which is inside the tan inverse function, that is y by x. Partial derivative with respect to x, it becomes minus y by x square. Now this one getting cancelled, you will get here we need to simplify. That is x square by x square plus y square multiplied by minus y by x square. So x square getting cancelled, you will get the resultant value as minus y by x square plus y square. Similarly, in the same way, we will find the partial derivative to v with respect to y as x by x square plus y square. Now we will substitute these first order partial derivatives into the Jacobian matrix. So we will get, this is determinant of 2x, 2y. This 2x represents ux, 2y represents uy. So second row, this is represents vx and this one is represents vy. So its determinant is equal to 2. Hence, the determinant of u comma v with respect to x comma y is not equal to 0. Hence, we will say there is no relation between u and v. It means u and v are functionally independent. Now we will see one more example. Related to functionally dependence. If it is functional, if you proved functionally dependent, our aim is to find what is the functional relation between these three functions. Now what is given? U is given x plus y plus z. V is xy plus yz plus zx, and W is x square plus y square plus z square. Then what it shows, here we have three functions involving three independent variables x, comma y and z. So three functions involving three independent variables. First of all, we will find all possible first order partial derivatives with respect to x, comma y, comma z. From u, the partial derivative of u with respect to x is 1. From u, the partial derivative of u with respect to y is 1. And from u, its partial derivative with respect to z is 1. Now coming to v, the partial derivative of v with respect to x. Here, if you are taking v value, v is equal to xy plus yz plus zx. Partial derivative with respect to x means you need to treat remaining two variables y and z, both are constants. So here you will have the derivative of x is 1, y is constant, take out common from the expression. Here the derivative of x is 1, z is constant. So you will have two terms y plus z. So the partial derivative of v with respect to x is y plus z. Similarly, we will find the partial derivative of v with respect to y. You will get z plus x. Similarly, the partial derivative of v with respect to z is x plus y. In the same way, we will apply partial derivative to w with respect to x, comma y, comma z. So the partial derivative of w with respect to x is 2x. The partial derivative of w with respect to y is 2y. And the partial derivative of w with respect to z is 2z. Now we will substitute all these first order partial derivatives into the Jacobian matrix. Here we will see the partial derivative of u with respect to x, y, z in first row. Here, sorry, this is v, this is v. Second row, the partial derivative of v with respect to x, comma y, comma z. And third row, the partial derivative of w with respect to x, comma y, comma z. Now substitute the respective values. Substitute the respective values. We will get this matrix. Now here we need to find its determinant. What is its determinant? 1 multiplied by x plus y into 2z minus 2y multiplied by x plus y minus 1 multiplied by 2z into y plus z minus 2x into x plus y plus 1 into y plus z multiplied with 2y minus 2x into x plus y. Now simplify this expression, you will get answer as 0. It means the Jacobian value is equal to 0. Therefore, we can say there is a functional relation between u, comma v and w. Now, if you are observing the Jacobian is 0, hence our aim is to find what type of relation will exist between u, comma v and w. If you are observing these three functions, apply whole square on both sides of u. Then what you will get? U square is equal to x plus y plus z whole square. X plus y plus z whole square can be written as x square plus y square plus z square, that is w, plus 2 multiplied by bracket start xy plus yz plus zx. So we can write directly by applying square to u, you will get a relation, that is w plus 2 multiplied by V. So once if you decided the Jacobian is 0, then we can say definitely there is a functional relation between U comma V and W. This is how we can write the relation between U comma V comma W. Now these are the some worksheet problems you need to practice. Already given how to find the Jacobian. Based on the Jacobian value, you can write the conclusion whether U comma V are functionally dependent or functionally independent. Once if you decided the functionally dependent, you need to express what are the relations between them. What are the relations between them like this. If determinant is not equal to 0, then you can write directly the functions are independent of each other. So till now I explained about the definition of Jacobian, in which two functions involving two independent variables. Similarly, three functions involving three independent variables. It means the number of functions is always equal to number of independent variables. Then only you will get a square matrix, the determinant is possible. Later I explained about functionally dependence based on the Jacobian value. If the Jacobian corresponding to the given functions is equal to 0, we can say the functions are depending upon one another. If not, we can say the functions are independent of each other. Thank you one and all.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.